Now we discuss finding eigenvectors. Let's begin with a definition. Let's suppose A is an n by n matrix and lambda for A, an n by n matrix, and lambda, an eigenvalue of A. Okay, then what I'm defining is the eigenspace. Associated to lambda. And this is denoted E lambda. This is the kernel of A minus lambda I. Okay, another way to say this is that E lambda is the set of all x in Rn such that Ax equals lambda x. And the most important observation to start off with today on our Finding Eigenvectors Day is that non-zero vectors in E lambda are precisely the eigenvectors associated to this eigenvalue. Well, another thing that we can observe is that E lambda is a subspace of Rn. That would not be terribly hard to check that 0 is in E lambda. Well, it's a kernel, right? I was going to just look at it from this definition, but E lambda, without a doubt, is a subspace of Rn because it's the kernel of a matrix. Okay, now we move to this half of the board, which maybe I will continue. Put my box like this. This is the one example last time where I actually found, I found for each eigenvalue, the eigenvalues were -1 and 6, I found one eigenvector. So I wrote out A minus lambda I, this matrix, and then I found one vector in the kernel. So V here is an eigenvector for eigenvalue -1, and this V is an eigenvector for eigenvalue 6. Well, in this new language of eigenspace, we see here that E minus 1 is the span of this one vector. And we see E6 is the span of this vector. And we could continue this example, right? If we go back, and we will do this today, we're coming full circle, you could say. If we go back to why do we even, or one reason why we even care about eigenvalues and eigenvectors was diagonalizing a matrix. And from these eigenvectors and these eigenvalues, and in this example, we could write here this would be the diagonal matrix. We put the eigenvalues along the diagonal. And then this matrix, we put or one eigenvector for each eigenvalue in the appropriate column. So here I would put this one, and here I would put this one. Here, well, that this B and this A are similar matrices. You can check that, but also some things we talked about at the very end of the last video. You notice the trace of B is 5, same as the trace of A. And the determinant of B is -6, same as, let's see, the determinant of A. Okay, what I will do now is I'm going to go through a few of the examples we had yesterday where we already found the eigenvalues, but now we're going to find a basis for each eigenspace, and if we can diagonalize the matrix, then we will. And here's the first one. These were the eigenvalues we found, even if I didn't do the same example from last time. When you have, and we discussed this, when you have an upper triangular or if you have a lower triangular matrix, the eigenvalues are along the diagonal. So we would be able to spot this even if we hadn't done this example. But let's go through. So we have three distinct eigenvalues for this 3 by 3 matrix. What we need for each one is a minus lambda I. So this is for lambda equals 1 here. We get the following. We have 0, 3, 4, 0, 2, 2, and 0, 0, minus 2. How do we find the kernel of this matrix? In theory, reduced row echelon form, right? And I could do that here. However, I don't need to in this particular example to find the kernel. What you notice here is that we see for this matrix, the rank is 2. Just by looking at this, we have, for example, 1, 2 linearly independent columns. It'll give us the rank is 2. And then, so this means the kernel has dimension 1. And so all I need to do is find one non-zero element in the kernel and it will be a basis. And you can see just by looking at this that, let's see, this would be E1 will be the span of just this one vector. We have 1, 0, 0. Okay. For the next eigenvalue, we see a minus 3i. What is this matrix? We get minus 2, 3, 4, 0, 0, 2, and 0, 0, minus 4. Now, again, this matrix we see, for example, 1, 2 linearly independent columns. This matrix has rank 2. The kernel will have dimension 1. And I could, in fact, it's not that hard to get myself to reduced row echelon form here. But if you notice, we absolutely must have, maybe I'll write what I said. This must have dimension 1, again, because this matrix has rank 2. If we have this and the kernel, this means we must have x3 is 0. Looking at really either one of those two equations, and then we get, let's see, the first equation, that x3 is 0, would say that 2x1 is 3x2. Okay, so then I get that E3 will be the span of this one vector where I could make x1, 3, and x2, 2, like this. For the last eigenvalue, lambda is minus 1. I get a plus I, and this will equal 2, 3, 4, 0, 4, 2, and 0, 0, 0. This one's not as quick to solve. Here we immediately got x3 was 0, and it was not too bad to solve x1 in terms of x2. Here we got immediately x3 and x2 were 0. On this matrix, I think I will reduce it to reduced row echelon form because it'll make my life a little bit easier. Okay, here we go. I will do two steps at once. I'm going to take 1/4 row 2 and I'm going to take 1/2 row 1 because they don't interfere with each other. So I'm going to make I'm going to make this one and this one. I get 1 3/2, 2. I get 0 1 1/2. And then I really only need one more step to be in reduced row echelon form. Maybe I'll do it here. I'm going to take 3/2 minus 3/2, excuse me, row 2, add it to row 1. This gives me 5/4, oops, 5/4, 0, and 1. Now we see, well, x3 is free. If x3 is, say, t, then we get x2 is negative 1/2 t. We get x1 is negative 5/4 t. Maybe the easiest thing to do to not have fractions, I will just take a, let's see, you can take t equals 4, for example, to get one element in the kernel, one non-zero element in the kernel, I should say. If I take this as 4, then x1 is minus 5. And here is minus 2. Okay. So we have done part of this, right? We found a basis for each eigenspace. Here they are. Now the second part is diagonalize, A if you can. Well, we can. It's even not that hard to see that this vector, and this vector are literally independent. And so they will go into the columns of my matrix S. So let us finish here. In fact, I have all of the work that I need just written in this part to diagonalize the matrix. We get S 1 0 0 3 2 0 minus 5 minus 2 and 4, and B, well, this is going to be 1 3 minus 1. We put the eigenvalues along the diagonal in the corresponding, the corresponding positions that came from where the eigenvectors were placed. So, for example, if I interchange these two columns, that would be another S I could use, and then that would just put this entry here and this entry here, right? So this 1 corresponds to this vector, 3 corresponds to this vector, and minus 1 corresponds to this vector, and this is how they are lined up. And then, if you want to check that AS equals SB. SB is So this is what I get for SB. Maybe I will leave it as an exercise for you, although it's not too bad. You just multiply that AS is also this matrix. So this S and this B are the diagonalization of A. We saw this last theorem, or this theorem, in the last example, and I want to discuss it now. it says that eigenvectors corresponding to different eigenvalues for the same matrix A are linearly independent. And a consequence of one, and I will prove one for two eigenvalues and associated eigenvectors, but a consequence of that is if you have a matrix that has n distinct eigenvalues, then it will be diagonalizable. And the reason this is a consequence is, well, you can find n linearly independent eigenvectors because these are all distinct. Those would make the matrix S, and then the matrix B, we would put the eigenvalues along the diagonal. And here you have a diagonalization of A. Okay, so let's prove where we have two eigenvalues of the same n by n matrix A, proof of one, eigenvalues of A, and let's say V1, V2, and their nRn with A V1 is lambda 1 V1 and A V2 is lambda 2 V2, like this. So I'm going to prove, number one, like I said, for two distinct eigenvalues, but really it's true for any collection of eigenvalues. If they're all different, then their corresponding eigenvectors are linearly independent. Okay, so how do I show that these two vectors, maybe I should write that, what I'm trying to show. Let's show V1 and V2 are linearly independent. Okay, how do I do this? Well, you assume you have some relation, some C1 V1 plus C2 V2 equals 0. And then we must prove C1 is 0 and C2 is 0. This goes back to how do we show two vectors are independent? So suppose C1 V1 plus C2 V2 is 0. And then we need to show, just like I said, C1 and C2 is 0. Okay, well, I'm going to work with this right here. And one thing that I can do is I will multiply both sides by A, let's see, A minus lambda 1 times I. So if we multiply by A minus lambda 1 identity, comma, we have A minus lambda 1 I times C1 V1 plus C2 V2 is, well, what's any matrix? This is some matrix times 0. Any matrix times the 0 vector is 0. So we get this is 0. Now I can rewrite this just using properties of matrix times a vector. This is A minus lambda 1I C1 V1 plus A minus lambda 1I C2 V2 is 0. Okay, so far so good. Look, what do we have? This here, there's only one option for what this is. This is 0 because V1 is in the kernel of this matrix and it's a subspace. So C1, V1 is also in the kernel of the matrix. Or you can also think, just pull the C1 out here and you get C1 times 0. Uh-oh. So this here must be 0. Okay. And then on this term, you see this is a difference of two matrices. This can be A, C2, V2, minus lambda 1, I, C2, V2, like this. Okay, rewriting, we have this, or we have this, A, C2, V2, minus lambda 1, C2, V2, hat equals 0. Okay, but now V2 is an eigenvector for A with eigenvalue lambda 2. As V2, maybe I'll write it this way, as A V2 is lambda 2 V2, we see here, this will be C2, lambda 2, V2. And I can factor something out here. So I can factor out a C2. This will give me a lambda 2 minus lambda 1, V2 is 0. Okay? But lambda 2 is not equal to lambda 1. V2 is not equal to 0. I'll say that in a sentence. Since lambda 2 not equal to lambda 1 and V2 not equal to 0, we have C2 must be 0. Once we have C2 is 0, we are basically finished, because then the original relation becomes C1, V1 is 0, but V1 is non-zero because it is an eigenvector. And so we get that C1 must be 0, okay? At the very bottom here, I'm sorry about this, but we have finished the proof. So what did I need to show? Look, it says show C1 and C2 is 0. Here we have C2 is 0, C1 is 0, and so maybe I will just say thus, V1, V2 are linearly independent. And this will, not only am I out of space, but I'm also finished with this proof. So what we see here is that 1 holds, even though I just proved it for 2 eigenvectors and 2 different eigenvalues. But then also we get 2. So anytime you have indistinct eigenvalues, you know the matrix is diagonalizable. Here's another example where we want to find a basis for each eigenspace, and if we can diagonalize A, then we want to. And it's another example from last time. So last time we calculated that we had lambdas 2, 4, 4. Algebraic multiplicity of 4 is 2. Algebraic multiplicity of 2 is 1. Okay. Well, this theorem we just discussed, we can't guarantee that this matrix is diagonalizable because we do not have 3 distinct eigenvalues. So let's go through and start with this part, find a basis for each eigenspace. First we look at A minus 2i. This is for lambda equals 2. We have 5, 0, 3. minus 3, 0, minus 3, and minus 3, 0, minus 1. Well, this is a matrix that we can quickly glance at. Look, we have 1, 2 linearly independent columns. Therefore, the rank of this matrix is 2. The dimension of the kernel will just be 1. And that means, maybe I should write that, the dimension of the kernel of this a minus 2I will be 1. And you can glance at this and find one non-zero vector easily in the kernel. Here. Oh, span. So I found a basis for this eigenspace, and now I have one more eigenspace. If a minus 4I, if the kernel of this matrix has dimension 2, equivalently the eigenspace for lambda equals 4 has dimension 2, then I know A is diagonalizable. I would have a total of 3 linearly independent eigenvectors. This one plus the 2 coming from here. On the other hand, if this kernel has dimension 1, then we won't have a diagonalizable matrix. Okay, well, let's do this now. A minus 4I is 3, 0, 3, minus 3, minus 2, minus 3, and minus 3, 0, minus 3. This is not in reduced row echelon form, but I'm not going to go through the steps. I will just say it's fairly easy in this case. You can do this in your mind. We just divide the first row by 3, and then we can have 0 and 0 in both of these columns, and then we would get here. That's pretty easy to see that this is when we move to reduced row echelon form. Now, what you notice, this matrix has rank 2. We're going to have a problem, but maybe before I discuss that problem, let's do this first part. We will find a basis for the eigenspace. Well, this also is not too bad to solve, especially because we have reduced row echelon form. It says that, first of all, x3 is free, and x1 will be minus x3. This will be minus t, and then x2 must be 0. So this matrix, this eigenspace is the span here. This is going to be 0, 1, minus 1. And you could check, make sure that this is in the kernel. Okay, looks good. We see here, okay, we only have 2 linearly independent eigenvectors for A, and this is the problem. So here, A is not diagonalizable. Because, well, if you tried, maybe, what color should I do this in? If you tried to make S, and you tried to make B, we know what B would have to look like. It would have to be like this, right? Put the eigenvalues along the diagonal. And then here we could put, here needs to be an eigenvector corresponding to 2, okay? An eigenvector corresponding to 4, so far so good. But then the only other eigenvectors we can find corresponding to 4 to put here would be something in here, which is only one dimensional. So this matrix S, if I find it, put another eigenvector, for 4, it will not be invertible. Okay, so the problem is we cannot diagonalize. okay, for this matrix. This leads to the following definition. For an n by n matrix A with eigenvalue lambda, the geometric, this is what I'm defining, geometric multiplicity. We talked about algebraic multiplicity last time. We get the algebraic multiplicity just by looking at the characteristic polynomial. But the geometric multiplicity of lambda is the dimension of E lambda. And the notation, maybe I'll do this part in black. This is what I'm defining. The notation is G mu. We had al mu for algebraic multiplicity. It's G mu. Okay, well, I find this entertaining. This is the dimension of the kernel A minus lambda I. Another way to think about this, and I've been stating this in some of the examples to help me realize I had enough vectors, is this is going to be, okay, n by n, good, n minus the rank of A minus lambda I. Okay, this is the geometric multiplicity, and as just to connect this to the example we just saw, in the last example, we had two eigenvalues. Algebraic multiplicity of 2 was 1. The geometric G mu of 2 is 1. We had the algebraic multiplicity of 4 was 2. And the geometric multiplicity of 4 was only 1. Okay, we had that in the last example. Now, this notion of geometric multiplicity, we can see exactly when a matrix is diagonalizable. Okay, and this comes in light of the last discussion we had. So theorem, a matrix, let me start off with n by n. Matrix A is diagonalizable if and only if the sum of the geometric multiplicities for eigenvalues of A is n. And that's pretty clear if you think about it. We have all of these eigenspaces, and each separate eigenspace, if you take a vector in one and a vector in another, they will be linearly independent. But if you have enough linearly independent eigenvectors in each eigenspace so that the total sum of the geometric multiplicities is n, or the dimensions of all the eigenspaces add up to n, then A will be diagonalizable. And this matrix S would be consist of the eigenbases for A. You just take the bases for each eigenspace, concatenate them into one big basis for, Rn. This goes in the columns S of this matrix. Now, one neat thing we get from this is immediately we can see sometimes that some matrices are not diagonalizable. And one of them comes that we did yesterday. This example, this matrix is not diagonalizable immediately. Diagonalizable. Because, well, we have only one eigenvalue. It's lambda equals 3. And this, well, the eigenvalue, this came from yesterday, computing the characteristic polynomial. But if we look at this matrix, A minus 3I, it's this, minus 1, 1, 0, minus 1, 1, 0, 5, 3, 0. In order for this matrix to be diagonalizable, we would need 3 linearly independent eigenvectors in the kernel of this matrix. That would say that the rank of the matrix would have to be 0. So this matrix does not have rank 0. This eigenspace does not have dimension 3. Or you could state this one more way, the geometric multiplicity of this is not equal to 3. Well, we know what it is. We have 2 linearly independent columns. This geometric multiplicity will only be 1, definitely not 3. And so this matrix is not diagonalizable just by this observation that we make. This example is not one that came from yesterday. So this one I will find not only an eigenbasis for each eigenspace as it asks me to, I need to start by finding the eigenvalues. So we need determinant A minus lambda I, which is 4 minus lambda minus 3, 0, 2 minus 1 minus lambda, 0, 1, minus 1, 1 minus lambda. Now, we have choices. It's very nice to have lots of zeros. And here we see this column has 2 zeros. This is what I will expand about. Plus, minus, plus, minus, plus. So this will be 1 minus lambda. And then this 2 by 2 determinant where I cross off this column, cross off, the bottom row. And I'm left here with just this 2 by 2. So this is 4 minus lambda minus 3, 2 minus 1 minus lambda. And if I keep going over here, I get 1 minus lambda times these two, 4 minus lambda minus 1 minus lambda, and then plus 6. And then let's see, one more step. I'll put this here. Or maybe we have 2 more steps. I need to, so just like we did last time, I want to leave this term. It will help me. You don't want to multiply it in and then have to refactor because factoring a cubic can be challenging. So I have a lambda squared. Then I have plus lambda. Then I have minus 4 lambda. Then I have minus 4 plus 6. 1 minus lambda. I have lambda squared minus 3 lambda plus 2. And now I am really at my final step. This will factor into minus 2 minus 1. So I have 1 minus lambda, lambda minus 2, lambda minus 1. Or I could have written this as 2 minus lambda and 1 minus lambda. It's fine this way. But what we see here, we see our eigenvalues. There's 2 of them. So this matrix, we see lambda is 1, algebraic multiplicity 2. Lambda is 2, algebraic multiplicity 1. Maybe I will write that above and then I will save, I'm going to erase so I can save my space. We know what we need to do. Find a basis for each eigenspace, diagonalize the matrix if we can. We have eigenvalues 1, 1, and 2. And it's not guaranteed just by looking at these so far. We don't know yet if A is diagonalizable or not. We have to look at the eigenspaces. Okay. Here we go. A minus I. This is for eigenvalue 1. This will be 3 minus 3, 0. Let's see, I'll make this a little smaller. This will be 2 minus 2, 0. This will be 1 minus 1, 0. Oh, look, this will be very nice. We see a rank 1 matrix because, well, there's only one linearly independent column, for example. And so this says the kernel of this matrix will have dimension 2. So we will have geometric multiplicity of 1 will be 2. So let's do this here. In fact, I really only have one. I'll just write it this way. You can do this all at once, or I will do it all at once. It's going to be 1 minus 1, 0. So here, what's a basis for the kernel of this matrix? Well, x3 is some t free, x2 is some r free, and then we get that x1 is the same thing as x2, r. So a general vector in the kernel looks like r, r, t, which is r 1, 1, 0 plus t 0, 0, 1, and now we see, I'll write it over here, E1 is, we have the following 2 vectors as a basis. And you can check, for example, that both of these are in the kernel of this matrix. Now we look at A minus 2I this will be 2 minus 3, 0, 2 minus 3, 0, 1 minus 1, minus 1. Maybe I will interchange the, I'm going to do 2 steps at once. I'm going to do this, 1 minus 1 minus 1. And then I will do 2 minus 3, 0. And then, okay, you should see what I did in these 2 steps, okay? We've been performing row operations all semester, but I just interchanged 2 rows, and then, for instance, I see 2 of the same row, you can add, subtract 1 from the other. Now, what will I do next? I'll come down here. I will take this one, I'll label. I'm going to take 2 row 1 minus 2 row 1, add it to row 2. This is the same for the moment. I get 0, I get minus 1, and then I get 2. Multiply through by minus 1 is 1 step, and then add, technically it's 2 steps, but I will do them as 1. Then I will be in reduced row echelon form. So this will be this. And then, for instance, I can add this row to this one. I get like this. This matrix is now reduced row echelon form. So maybe this final thing I'll just label. I did 2 steps, and this arrow and this arrow were 2 steps, but I think we're okay at this point in the semester. Okay, so what I get here, x3 is free, say it's t, and then x1 is 3t, and x2 is 2t. Okay, so now I can write, I'll do it up here, say E2. Well, I know it's only going to have one vector. This matrix, we see the rank is 2, so the kernel has dimension 1, and this will be the span. This will be 1, 3, and 2. Oops. Okay, we have 3 linearly independent eigenvectors. In fact, A is diagonalizable. So let me see if I can make a box just to finish this problem here. A is diagonalizable. The S matrix and the B matrix, and then I'll say one more thing after this. Oops. Well, my eigenvalues are 1, 1, 2. And then I put 1 here and 1 here. And then corresponding to 2, I use this one. Okay? So here is the diagonalization of A. But then there's one more thing I can say, and maybe I'll erase the eigenvalues here at the top just to connect it with the language of last time, an eigenbasis for the matrix. This means it's a basis for R3 consisting of eigenvectors of A. Well, we just concatenate. So we have 1, 1, 0. We have 0, 0, 1. And we have 3, 2, 1. Okay, like this. So this is an example, and sometimes this happens even though we only had 2 distinct eigenvalues. The matrix A is still diagonalizable. In fact, here we see the geometric multiplicity of 1 is 2. It's the same as the algebraic multiplicity of this eigenvalue. Comment I will make after this example, and also the theorem that we talked about geometric multiplicities, for any, let's say, lambda eigenvalue of A, it's always the case that the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity of lambda. And we saw, well, we've seen one example where we had one strictly less than, and the matrix was not diagonalizable. In the example we just did, we saw where the geometric multiplicity and the algebraic multiplicity were the same when we had one with algebraic multiplicity 2. Now, I will end today with a kind of a neat example. Oh, I'll call it a theorem. For any n bigger than 1, there exists a n by n matrix A that is not diagonalizable. Well, in fact, there are infinitely many, but I'm just stating this as there exists one. Now, let's put this in light of something that came up last time. One thing I mentioned is if you have if n is even, you can find an n by n matrix A that has no real eigenvalues. And well, we found a 2 by 2 2 videos ago, but you could create a 10 by 10, 20 by 20, 30 by 30, any of that with no real eigenvalues. But this is a little bit different. This is for any n, even or odd, you can find a matrix that's not diagonalizable. So maybe my proof, this is a there exists theorem. So the proof is I just got to give you one, right? But I'm just going to show you for n equals 5. Of course we know an example for one n is not a proof for all n, but you can look at this matrix and do the exact same one for general n by n. I'm just going to write it out for n equals 5. So I'll just write this. I'm proving this for n equals 5 only. Well, let me give you a 5 by 5, and I chose 5 because it is odd. So it does not, we know, for instance, whatever I write down, 5 by 5 matrix, is going to have at least one real eigenvalue, without a doubt. Okay. Here's my 5 by 5 matrix. We have 2's along the diagonal. Then I have 1's on this right above and 0's everywhere else. Well, the first thing that we realize is it's upper triangular. And so this means that the eigenvalues are along the diagonal, and it's the exact same thing. So we have lambda equals 2 is the only eigenvalue, but we could write it like this, where the algebraic multiplicity of this is 5. But what is a minus 2i? A minus 2i equals. Here's a minus 2i, and you notice this matrix has rank. Well, this matrix is already in reduced row echelon form. Okay, it has rank 4. Immediately we know the geometric multiplicity of 2 is 5 minus 4 is 1. And it's not 5 as it needs to be. And so we get that A is not diagonalizable. And even though, as I mentioned, I proved this theorem, this there exists for n equals 5, you could take the exact same matrix, well, not the same matrix, the same construction. You could put any number. I just chose 2 down the diagonal, but put 1's right up here, and you will get a matrix that's not diagonalizable by the same argument.